Welcome back to our video lectures on the course Material Science and Metallurgy. In today's topic, we will discuss on the crystal structures of metals. If you look at the overview of today's presentation, so first we will review on the crystal systems topic what we have discussed in the last video lecture. Then we will discuss about the crystal structures specifically for the metals. Then some of the important definitions we will see, the two important characteristics. One is the atomic packing factor, then another one is a coordination number. So these two we will see. We will try to calculate the atomic packing factors and crystal structure, atomic packing factors and coordination numbers for a particular crystal structure. So that is a simple cubic structure we will see today. So if you recall quickly what we have discussed about crystal structures, first we have defined lattice. A lattice is a three-dimensional array of points coinciding with atom positions. So as you can see it here, so these are the points that we have considered in the three-dimensional space. So here is a one more point. So here one more position and one more position and one more atomic position, and similarly here, here and here. So like this in the three-dimensional array of points. So this is called as lattice, crystal lattice. And the fundamental building block, that is this fundamental building block that is considered, that we defined it as a unit cell, right? And the corners we have placed it, the atom positions are considered in the corners, right? So likewise, if you have chosen one particular unit cell, so based on the axial lengths, that is A, B and C, that is in the x direction and y direction and in the z direction, the axial lengths of the unit cell and the axial angles, that is alpha, beta and gamma. So alpha is here and beta is here and gamma is here, the angle between the three coordinate axes. So based on the relationship between axial lengths and axial angles, so we can we have categorized crystal structure into 7 crystal structures. So total 7 crystal structures. One is a cubic, then tetragonal, then we have discussed hexagonal, orthorhombic, then we have monoclinic, orthorhombic and triclinic. So these are based on the relationship between axial lengths and axial angles. So similarly, so August Bravius is a French scientist who proposed, based on the positions of the atoms within these crystal structures, we can receive 14 lattices that are possible, and so these lattices we call it as a Bravius lattices. So total 7 crystal systems and 14 crystal Bravius lattices that are possible. So something like a primitive structure where atoms are being placed at the corners of the unit cell. Then we have the body centered one along with the atoms positioned in the corner of the unit cell. So one complete atom will be situated at the right center of the unit cell. That is called as a body centered structure, cubic structure. This is a cubic crystal system. And similarly, we have the face centered one. That is, if you look at for this particular cube, so we have 6 faces. On each face, at the center of the face, you have placed an atom. So like this, based on the atom positions, we had 14 Bravius lattices that are possible for these 7 crystal systems, right? Now, if you come to the metallic crystal structures, so in general, metals crystallizes into 4 forms of crystal systems. So first one is a simple cubic structure. This is a simple cubic structure. Then we have the face centered cubic structure. Then we have body centered cubic structures, some of the metals also forming hexagonal closed pack structure. So SC, FCC, BCC and HCP. These are the common crystal structures that these metals will be crystallized into. Its atoms will be positioned in this among these 4 crystal structures. So if you look at simple cubic structures and discuss about the positions of the atom, so here is the illustration. So in this, you see I have considered an unit cell where on each corner of the unit cell that is been positioned with the atom. So this is the atom. So there are 8 corners like this, 1, 2, 3, 4, 5, 6, 7, 8 corners. On the 8 corners, I have placed 8 atoms in this unit cell, and this is a simple cubic structure for this particular cube, that is a unit cell. On the corners of each cube, so there are 8 corners, and 8 corners I have placed 8 atoms in the corners. So this is a simple cubic structure. If you look at the example, the only metal that is present in the simple cubic structure is a polonium. It is polonium. Polonium is a only metal that is present in simple cubic structure. Then come to the face-centered cubic structure. So this is a face-centered cubic structure. This is a unit cell. On every corner of the cube, an atom is placed. These are the atoms, corner atoms, right? Then we had so this is a face. So this is a face, right? So this is one of the faces, right? For this particular face, at the center of the face, I have positioned another atom. Right. So like this, there are 1, 2, 3, 4 and 5 and another 1, 6. Total 6 phases will be there for the cube. For the 6 phases, I have positioned 6 atoms at the center of the face. Right. All these are center of the face. I have positioned 6 atoms. So this is how atoms will be positioned in the face-centered cubic structure. This is the simple unit cell illustration, and you can look at how the amount of atom that is being shared for a one particular unit cell has been illustrated here, right? In the three-dimensional space, how we will be considering the atoms, how atoms are being positioned can be noticed here. There is a systematic placement of the atoms according to this positions. Then if you look at examples for this face-centered crystal structure metals especially. So aluminum, you call it aluminum. Then we have the copper. Then gold is also having a FCC structure, iridium, lead, nickel, platinum, silver. There are so many metals that is present in FCC structure, that are having FCC crystal structure. And if you consider the iron in the gamma iron, so gamma iron is also having the FCC structure, right? So this is about the face-centered cubic structure. Then if you look at body-centered cubic structure, so this is your unit cell. At each corner of the unit cell, you have considered one atom, so that is there. So on the each corner, you are having one atom. Then at the center of the unit cell, the entire atom is being considered. At the center of the unit cell, you have considered one complete atom. So if you look at the share of the atom for a particular unit cell can be illustrated, where you can see a complete atom. You see one big atom, the complete atom is placed at the center of the unit cell. So this is a body centered. So since this is a body centered cubic structure, BCC. The three-dimensional illustration is presented here. You can look at, so this is your unit cell that we have considered here, right? So if we discuss the examples which possess the metals which possess this BCC structure, that is lithium. We have the lithium, sodium, potassium, chromium, barium, vanadium and alpha iron. Previously we had gamma iron is in the FCC structure, but alpha iron will be present in the BCC structure. So this alpha iron up to 727 degrees centigrade, up to that. So this alpha iron present in the BCC structure. So later it will be converting into the gamma iron, and the crystal structure also will be changing from BCC to the FCC crystal structure. Then we have tungsten. Tungsten is also having BCC crystal structure, and many more. Then another structure, that is hexagonal close pack structure. If you look at hexagonal close pack structure, so this is an hexagon. The base is an hexagon. So this is a hexagon. Okay, these are the front and top. We have the hexagon here, base and the top. So in between, on each corner of the hexagon, you have placed with one atom, that is their front and the bottom and the top planes, and bottom and the top planes, again at the center you are having face centered atoms, the two face centered atoms for the hexagonal face. Okay, then we have at the center of in between these two top and bottom planes, for the side among the 6 faces that you are having, so you have placed alternatively 3 atoms, face centered atoms alternatively. So this is the architecture of hexagonal close pack structures, HCP. So in the 3-dimensional, you can see this is the bottom layer, then we have the center layer, then we have the top layer of atoms that are being present in the HCP structure. So this is a hexagon, that one hexagon that you will be considering, hexagonal close pack in between. Some of the examples, the metals that possess this hexagonal structure, that is a beryllium, then we have cadmium, magnesium, titanium, zinc, zirconium. All these metals are possess this HCP structure, hexagonal close pack structures. So we have discussed a simple cubic structure with the example, the only metal. Thank you.